This is my first lab of Physics 1, and we will be talking about an object at constant velocity. So, straight into our table of contents, we're going to have an introduction to the experiment, and then we're going to look at the tracker analysis of a pencil, which is what I rolled, and then we're going to look at the computational model, and then compare the two and discuss. So, first thing, introduction, key concepts. First thing is Newton's first law, which is an object stays in motion if there's no net force acting upon it, and that translates to if there's an initial velocity and the F net is zero, then it will have a constant velocity. And then the velocity update formula, which is basically saying that same thing, that if F net is zero, velocity final will equal the velocity initial. And then the position update formula, which is saying velocity averaged over a period of time times time is going to equal a change in position. And then right into our experiment, some key assumptions that we make is that we ignore the force of friction, ignore air resistance, ignore rotational inertia. In this case, there would be rotational inertia because the object that I'm rolling is a pencil, and since I'm rolling it, there's going to be rotational inertia. Ignoring motion in the y-axis as well. We're only looking at x-axis movement. And then lastly, goals. Our goal is to basically just measure the motion of a pencil with no forces acting upon it, and we're trying to test the theory that a constant velocity is there if there are no net forces. So straight into the free body diagram. As you can see, while the pencil is kind of moving by itself, the only force on it is the normal force and the force of gravity, which both cancel out. And basically, the situation here is that I pushed the pencil, and then after that, I kind of let it go by itself. So it came in with an initial velocity, and that initial velocity should stay constant throughout the video. The system is a pencil, and the surroundings are the table, air, and the earth. So this is my tracker analysis. As you can see, this is me. This is like a frame of the pencil rolling, and I kind of just used the points to kind of track it as it goes along. This is the position versus time graph. As you can see, it's not perfect slope, but it's pretty close. And then these are the individual points. And then as for the computational model, basically I just took the initial recorded velocity and assumed it to be constant throughout. So we kept that initial velocity that it had and then assumed it to be constant. As you can see, it's a perfectly straight line because each iteration led to a constant slope, since we assumed there was no net force. So when we would use the velocity update formula, it would never change, and the position would update by the same amount every time. And then going back to this now, so these are both the graphs compared, the computer data and the tracker analysis. And as you can see, the computer data is completely straight, while the blue dots are a little bit off that, starting to diverge towards the end. And yeah, so I think the reason they diverge towards the end is because of the things that we assumed, I believe, such as no friction or no air resistance. Obviously, in the real world, there would be friction and air resistance. Some possible errors are also there could be a human error while tracking, and then there could also be motion in other directions that was not accounted for in the video. And then as for the what ifs, if the axes x and negative x were flipped, I think the pencil would be moving in the negative x direction, and the observed and calculated velocity would be negative, since those are both vectors, but the magnitude would remain the same. And then as for, is it possible for me to say how many forces are added together to give a zero net force? No, I just think that there's too many types of forces that could be acting on the pencil. Just a few that I mentioned, and then on top of that, there could be a tilt of the table. There could be bumps on the table. I think there's so many different things that we couldn't account for, but we can get pretty close. In reality, obviously, there's no net force of zero on the pencil. It's probably just pretty close. So, yeah, thank you so much for listening, and have a great day.